Spring with a natural length L hangs vertically. Okay, it hangs vertically. A block is attached to the spring and held in place such that the spring length is still L. So what do you do now? We attach a block and we just hold it. So you're holding it with your hand here. It's still L. You attach the block and hold it so that still the length is L. The spring is neither stretched nor compressed. Now, when the block is then released, then you let go. You're holding it with your hand, you release the block. You let go. It is found that the maximum length of the spring, that the maximum length the spring attains is L plus 0.1 meters. So what is found is that when we let go, the maximum length the spring attains this is the maximum length. It will oscillate. Okay, it will move up and down. But the maximum length the spring attains is L plus 0.1. So this is 0.1 meters. So in other words, it is found that when we let go, the object falls down 10 centimeters before it starts moving up again. So the maximum length of the spring is its original length L plus 0.1 meters. The spring oscillates, and the question is, what is the period of oscillation? Now, we know that for the spring, we know that omega is the angular frequency is square root of k over m. And we know that the period t, 2 pi over omega, so it's 2 pi square root of m over k. M is the mass of the block, and k is the force constant of the block. Now, we are not given here, we're not given m, we're not given the mass of the block, and we are not given the force constant, k. So we don't know m, we don't know k. All we know is this, that when you release the object, that the maximum distance it falls is 0.1 meters before it starts moving up again. Okay, so how do you solve this problem? Notice this is released from rest. So V here is 0. And when it reaches the maximum compression, so it can't go any further down, it means also that its V is 0 here. If the velocity here is not 0, it will continue to move down. So I can apply conservation of energy. I can apply the energy here. EI is equal to EF. The energy here, the kinetic energy is 0. Ki plus Ui. I can measure the heights from here. The kinetic energy here is 0, but the potential energy is m, g, h. And h is 0.1. So this is m, g times 0.1. This is the total energy of the object here. E final, when the object is here, the kinetic energy, again, its velocity is 0, so the kinetic energy is 0. The height of the object now is 0, because it's measured from here. So the potential energy is 0. But the spring is extended. It's extended by h, which is 0.1. So the spring being extended, there's a potential energy in the spring which is half kx squared. X is the extension. How much is the extension? H, the height h, which is 0.1. 0.1 squared. Equating the initial and final energy, I have m, g, h, let's just put h for now, which is 0.1, is equal to half k h squared. So the h cancels. I get mg equals half k h, which means that m over k is equal to h over 2g. M over k is h over 2g. Now, h is 0.1, and this is 2 times 9.8. So this is 0.1 over 19.6, which is 1 over 196. This is m over k. So what is the period t? 2 pi square root of m over k, so square root of 1 over 196. What is the square root of 196? 14. 14 squared is 196. So this is 2 pi over 14 seconds. Again, 2 pi is 6.28 over 14. So this is about 0.43 or 4. About 0.4, this is 0.45 seconds, approximately. So this is a period of oscillation of the block spring system.